Today's problem comes from a viewer, and it says 3 points are being chosen at random on a circle. A triangle is formed by connecting the 3 points as vertices. Find the probability that the triangle is obtuse. Okay, so 3 points on a circle, I mean, obviously it's kind of implied here that we're taking a uniform distribution of the points in the circle. My first thought here is that it doesn't really matter where the first point is, so I may as well just say that the first point is at the top of the circle, and then the other 2 points get generated randomly. So we can do, if we have 3 points at random, we can always rotate the circle so that one of the 3 points is at the top. So there's really only 2 points being chosen randomly. The first one is at the top. And then the other thing that I think is kind of important here, or might be a key, is that we're looking for an obtuse triangle. So in particular, we want one of the angles to be greater than 90 degrees. And for a triangle inscribed in a circle, if one of the angles is 90 degrees, then the opposing side will be a diameter of the circle. Let me draw a diagram so we can see exactly how this works. Okay, so if I have a point, if I have a diameter of the circle like this, so this point goes, this side goes through the center. So if that's the center of the circle, then this is 90 degrees. And if I move this point around the circle in that direction, then this angle will become greater than 90 degrees. If I move it this way, it'll become less than 90 degrees. So what I want to try and do here maybe is phrase the problem as, I think the triangle being obtuse will be the same as all 3 points laying on one half of the circle. So if all 3 points lie above a diameter. But I need to think about that for a second. Now that I think about it, I think I've seen a similar problem to this. I've never worked through the solution myself. Another equivalent way of phrasing this problem is whether the triangle contains the center or not. Right? If the 3 points are on the circle, I should mark the center here because it's going to play an important role in this problem. If the 3 points on the circle are chosen such that the triangle contains the center, then this will not be an obtuse triangle. But if the 3 points, if the triangle does not contain the center, then this will be an obtuse triangle because one of the sides, that angle there would have been greater than 90 degrees. But I wonder if it's best to think of this problem as whether the triangle contains the center or not, or whether all 3 points lie on one half of the circle. Like if all 3 points, if I draw an arbitrary diameter here, like this, if all 3 points lie above, then it'll be an obtuse triangle. If all 3 points lie below, it'll be an obtuse triangle. I just need to think about the best way to sort of formulate this and see if there's maybe there's a simplification to the problem that it turns into some really easy event that we're trying to compute the probability of. Or maybe there's an easy, I don't know if we can reduce this to a nice integral to compute. I don't even know now if my original convention of putting the one point at the top, I don't even know if that's necessarily going to be the best way to sort of normalize things. But let me work with this for now. So I draw 2 points. So the sort of problem with this is that if I want to think of everything being on one side of the diameter, or on one side of the circle, then the ordering of the points matters, right? If one point happens to be, well, I guess there's no tech on the circle, there isn't really a sense of one of the points being in the middle. Although intuitively we would say that if the 2 points were there and there, then the one at the top is in the middle. Right, because I could draw a diameter like this, and then we're looking for the probability that the other 2 points lie anywhere above the diameter, but that's for this particular diameter. What if instead the diameter looks like this? Actually, maybe I'm onto something here. Maybe this will work. I'm going to think for a second. If I draw an arbitrary diameter, like that. So this is condition on a particular diameter. I just need both points to lie on the same semicircle. I need both points to lie on the same one the original point is. Okay? So I draw 1 point that has a probability of a half being above or on the same semicircle. I draw another point that also has a probability of a half being above. These are independent. So that would be 1 over 4. If I draw a different diameter, if I draw a completely different diameter, then again, oh no, this doesn't work, right? Because 1 point could be there and 1 point could be there. They are, so it's not for a fixed diameter that I need them to be above. There is a diameter where it's above. Okay, I need to think about this a little bit more. So another way I could potentially do this is, each point is, of course, just for now, I'm gonna sort of renormalize things and say that the first point is there. And the reason I'm doing that is because every point now can be parameterized by the angle that it makes here, theta. So if this is the first point we draw, theta 1, we have another point here, P2, and that's theta 2. What I could do is find the condition on all ordered pairs, theta 1 and theta 2, that satisfy that the points will make an obtuse triangle. And then, find the area of the set, right? Find the area of the set of admissible thetas divided by 2 pi squared. What if, so another thing I'm thinking now is, okay, let's go back to my original convention. The first point's at the top. We draw the second point. Okay. Now, condition on this point being fixed, what is the probability that I have a success? Well, if I draw P2, this might be the way to go. So as long as the next point lies anywhere there, it'll work. Right? I think this is going to be the easy way to do it. I think this is gonna work. Let me draw my diagram a little neater because I think this is going to be how I go about this. Okay, so there's my reference point. There's the center. Now, suppose P1 is here. I'm going to draw a couple of diameters like this. Okay. If the next point, so this is the area that's sort of off limits, because if the third point is there, then this triangle contains the center. It will not be an obtuse triangle. But if the other point is anywhere outside of this shaded region, if I'm over here, then this angle at the top, the angle at the top will be greater than 90 degrees. And if I'm over here, the angle at P1 now is greater than 90 degrees. If I'm here, right, that triangle is certainly an obtuse triangle. And so if I fix P1, let's call that theta 1 for now, then the probability, oh, and of course this is also theta 1, then the probability of success, so probability of success conditional on theta 1 is 2 pi minus theta 1 over 2 pi. I like to often think of things in extremes, so let's think about the extreme cases. One of the extreme cases is when P1 is extremely close to this reference point. Okay, so I'm claiming that then this is the only region that's off limits. Right? That'll clearly give an obtuse triangle. This will give an obtuse triangle. Yeah, and the only way for the triangle to contain the center is if the other point lies in this small region here. So if theta 1 is very small, the probability of success is big. Okay, so this is the probability of success condition on theta 1. And do I, what do I need to do here? Do I just need to integrate this from 0 to 2 pi or something like that? Okay, before I sort of confirm this for sure, I want to also check the other extreme case here. Because, you know, now that I think about it, I'm working, I might have to go through some of these computations again. I'm working from 0 to 2 pi, but maybe I should have parameterized this from negative pi to pi. Like, Yeah, I might have to redo some things here. Okay, let me draw this diameter again. If P1 is here, then we have success as long as we don't land there. So what is the length of that region? That'll be 2 pi minus pi over 2. Or yeah, 2 pi minus pi over 2. Now, if theta is greater than pi, okay, yeah, this, I'm not going to do it this way. The probability of success, conditional on theta 1, let's just call it theta. This is going to be 2 pi minus the absolute value of theta divided by 2 pi, where we now have to think of theta as being between negative pi and pi. Okay, if I go to my diagram, so this point corresponds to theta equals 0. As I move in one direction, you know, these are negative values of theta moving away from 0 all the way down to negative pi. And these are values of theta increasing from 0 all the way up to pi. But I'm concerned with the absolute value of theta. I'm concerned with the magnitude of that angle without considering positive or negative. So the absolute value of theta, right? Like if I'm very close to pi, if theta 1 is, say, if theta 1 is very close to negative pi, then I'm here. Yeah, I have basically like a 50% chance of success in this case, right? Because so that theta, that's theta there. As long as my third point is over there, I'm happy. So I'm not allowed to be anywhere over there. And that's about 50%, slightly less. Okay. And theta was negative there, right? Yeah, theta was a negative number. Okay. So I'm not really confident in this. I mean, maybe it'll turn out to be a half anyway. But let me integrate this now. So now my probability of success is 1 over 2 pi. Integral from negative pi to pi of 2 pi minus absolute value theta over 2 pi d theta. Yeah, okay. 3 over 4. But is this reasonable? Like, this is saying that most triangles that you make this way do not contain the origin. I don't really want to spend a huge amount more time on this. I'm, you know, with my reparameterized things, my reparameterized version of the points with theta between negative pi and pi, I'm pretty confident that this is the right approach. I don't know if I've made an error in the integration here. I'm more concerned with whether I have the right approach here. But just intuitively, like, do 3/4? Maybe this is right. I'm trying to wrap my mind around intuitively why, like, this number, just intuitively, this number seems too big to me. But, you know, if the math is correct, I trust the math. But I could probably argue to myself why the number is quite large, right? If I think about sort of the generic case, when I draw one point at random, there's a 50% chance it lies above this line. And if it does, then there's a pretty good chance, like now the set we have to avoid is down here, which is pretty small. So even if we have a 50% chance of the set to avoid being small, and if P1, in the extreme case, again above that diameter, but if P1 lies over here, then we have to avoid basically only 1/4 of the circle. So half the time we're successful 3/4 of the time, or better. If P1 lies below that diameter, which again happens with 50%, then, now I'm successful as long as I end up anywhere over there, which is about half. Yeah, I'm just, at this point, I'm just kind of dilly-dallying and trying to convince myself that this answer makes sense intuitively. I'm not going to waste your time going through this. I'm just going to say I would want to go back and recheck all of my arguments and all that kind of thing, but this is what I've come up with for now. I don't want the video to go on forever, so that'll be my final answer. But if I think about this on my own and I have more to say about it, I'll write it down in the description. Thanks for watching.